Weikeng.
Hi. Well, I'm now just like the research partner with the with venture capital. So let me firstly start that this is not like investment advice, and that so basically that like this year we see a lot of the thing related to interactive ZK, and I think that I can use this like presentation to kind of just show everyone what it is and what it has. So first of all, let's talk about this like note, interactive zero-knowledge proof. And that this is a cryptography tool, and it has three properties: interactive, zero-knowledge, and proofs. And what is actually the best? So a lot of people are saying that cryptography is very complicated. Can you try to explain to me in a simple way? And I find you the perfect picture for interactive zero-knowledge proof. And that's one. You can see I even provide you with the link. The idea with interactive zero-knowledge proof is that this is almost like a phone call, like a conversation. You talk with the other person, and that person being convinced that this is the case. And there are three properties. Interactive, this is like a phone call. Is that like, it's not like an email. You cannot write down. It's just a real-time conversation. It's zero knowledge, basically similar to what we do with Snark and like NIS. You can hide some information, and this is a proof. Basically means that the prover cannot lie about that. Okay. And we can actually have a simple comparison between what MPC, like IZK, and also NIS, basically what SNAR is, like between them. So you can firstly notice that like interactive zero-knowledge proof is actually a very special case of like MPC. If you have MPC, you can do whatever like IZK can do. IZK have some limitation. It only have two parties, a prover and a verifier. It only allow one party prover here to be the providing the data, while the verifier is just verifying. And that like anything IZK can do, MPC can also do. You can think that IZK is basically just a very special MPC protocol where one party is talking everything while the other party don't say anything. Now, I want to talk about another thing, that if we compare with IZK and NIZK, you can also consider SNARK to be a very special type of interaction, where in this interaction, you just need to, though the prover only say something, and the conversation ends right there. And that like MIZK is a little bit like email. You can also think about that. That's a very special case of the phone call where you say something and the other person hang off. Like so, anything that like you can do with like non-interactive zero-knowledge proof, you can clearly do that with the interactive zero-knowledge proof. Okay. But now here's the question. As I said, a lot of this thing IZK can do, you can use MPC. And if something can be done with like Snark, with MIZK, you can clearly also do that with MIZK. People will ask me the following question: why do you even bother creating the notion of interactive zero-knowledge proof? Wouldn't it just be MPC? The reason for that is that you do see something that's different there, is that interactive zero-knowledge proof is something that have a good performance. And this kind of make it worthy to kind of separate that from like the other notion. And when I talk about that is actually have a good performance, I should be able to give you a number. And in one of our paper, we actually like go over all the trouble of different platforms and kind of give you the number. If you are using interactive ZK, you can do one hour benchmark in about like less than 1 minute. If you use like NIS and Snark, you go up to something like 40, like basically you can see that the time quickly go up. MPC is also quite like inefficient. And you can see that when something goes to something like 45 times or like 100 times, this actually changed the thing significantly. Some application that was possible for user quickly become impossible. So this improvement actually is very significant, and that's why it's actually useful to separate IZK from other notion that being more restricted and being a more special case give you some like advantage that seems to be very important in real-world applications. Okay, but before I go into more, IZK is also not magic. It has some limitation, and the performance benefit sort of come from this like limitation. First of all, IZK can only be used to prove something. It's not multi-party computation. Multi-party computation, you can compute on data that like no one party know of that. Like you need both parties' input for that. IZK doesn't give you that. There is only one party providing the data, here Alice. And that like the other party also doesn't receive any output. The only output that the other party receives is that whether or not this is true. Another limitation of Claude is the interaction. Interaction made it a little bit difficult to be used on blockchain because now you cannot just post the proof on the blockchain. And in fact, actually that would not be useful because people will not be able to trust that proof. A third party, it's a little bit like videotaping, like phone call, is that you see this phone call in the video, you doubt whether or not they actually said that. And that's basically the interesting property of the interactive ZK. And this is almost a provable guarantee. Interactive ZK provides some sort of deniability, is that if you have someone record the transaction of the interactive ZK, because the protocol guarantee that people can fake this transcription easily, it actually provides you the deniability, which I will talk about that a little bit later. But basically that the requirement of an interaction is both an advantage and a disadvantage. And sometimes it might be useful for certain application, like in KYC. Okay, so now let me quickly go through what are the research about IZK. So first of all, when we are talking about zero-knowledge proof, the first several words of the zero-knowledge proof are all about interactive zero-knowledge proof. So the first paper, the second, the third, and the fourth, these are all about interactive zero-knowledge proof. And also in this paper, they prove a lot of the things. Like for example, is that everything you can prove have a zero-knowledge proof, and something similar to that. It's kind of later that people start to discover that, oh, we can have some sort of non-interactive zero-knowledge proof. And in Mikhali's paper, CS proof, which technically, people probably heard about paper like Fractal and so on, but basically they use the PCP theory right there. So basically that this kind of tell you about how to construct a snack. Early work of ZK is all about the interactive. And a lot of the important theory about what ZK can do, what ZK can do actually is about how much interactive ZK can do. Okay. But interactive zero-knowledge proof kind of not become very popular because we realize that we actually have non-interactive version of that. It's kind of until recently that people start to realize that interactive ZK can be done very efficiently, and this has something to do with what happened in around 2019 when people start to discover better oblivious linear evaluation that can be done with very little communication. And after that, you start to see in just a few years, by the way, you can think about this something very similar to 1986, where suddenly a lot of the important crypto papers appear in a few years. These three papers are arguably concurrent to each other. On the good side, they didn't cause trouble for each other to get accepted in the conferences, but that might happen as well. So basically that these three papers, almost at the same time, and have techniques that are slightly different with each other, that I'm talking about how you can actually build interactive zero-knowledge proof using this new thing called silent vector oblivious linear evaluation. And subsequently, this opened a lot of the research, even talking about that, oh, now we have interactive zero-knowledge proof. How can we, actually that's what they do now. What they do at that time. How do we get technology and optimization that people have been building on Snack and bring them to interactive ZK? And here is a few examples. The first paper talked about that, oh, we don't just need to multiply A and B, we can actually define polynomial. And a lot of the things that we do is not just multiplication gate, that's inconvenient, that's restricted, let's just define that over low degree polynomial. That gives you performance speed up. Then people also realize that, oh, I actually want to process the computation over different finite field. Another two papers, arguably concurrent with each other, also have shown that it's possible. And a recent paper also used technique that we discovered in, for example, GKR, or the Virgo paper, showing that you can actually, when you are handling computation that are repeated from each other, you also get a performance advantage there. Okay, and in the rest of the talk, I will focus on two papers. They each are a specific application. One is in submission. They are actually talking about how to verify Web2 data. Another paper that I will talk about is our paper is more about how to use IZK to discover bias in federated learning, the data part. Okay, so let me go to the first application. So when we talk about zero-knowledge proof, let's think about what are some zero-knowledge proof use cases that are in the real world. So I don't want to talk about oh, I know the function, I know the value of the hash function or something like that. What are something that we care about in the real world that we want it to be zero knowledge? Here are a few. You want to prove that I'm single, I have a job, I have saving, I'm a citizen. people may have the feeling that I might be dating. But that is basically what will be interesting here. Now, I kind of want to tell you why this whole thing could actually be proven today using incredibly zero-knowledge in some way. So actually, a lot of the things are available in Web 2, and you actually have ways to prove them. It's a little bit, there are actually a few companies that are already building solutions for this, but here I just highlight that why this is possible is because that you can use incredibly zero-knowledge to verify things that you see on like the web page. And you can see that like, oh, IRS, this show me a web page, and here you can prove that you are single by IRS website, the HTTP request show the word single there. There is a caveat of this though. It only shows whether or not you are single last year, but that like this kind of is already kind of useful here. And you can also verify whether or not you have income, right? And that like this is basically using the zero-knowledge to prove the following: is that proving first of all that you actually have this account, and second is to prove that IRS did say that you are single and you have the income. Another example, like you have saving, this is also easier. Just log into the bank's website. Banks always tell you how much you have. And like IZK provides a solution over like some API that are probably closed source or like are not widely available. For example, JP Morgan, although does have an API, you might not be able to get access to that. But IZK provides you a way that as long as the user installs a browser extension, which I think at least 2 companies already have that product, and that you can actually prove things on the internet. The last thing is about citizenship. Many people actually would be very interested on this, is that this can be used for KYC, right? Many people doesn't know that the passport have a chip, and this chip is NFC readable, and this chip have a digital signature of the country that issued the passport. So if you want to prove that you have a valid passport, there are many ways that you can do. You can use incredibly ZK. You can also even use a snap just to prove that, like, oh, I have a passport, that passport have me, right? And that there is already a paper that actually like talk about that, how do you do that? They actually have mentioned explicitly that like, yeah, the passport does have this like signature. They can actually use like zero-knowledge to kind of verify that. So you don't reveal everything on your passport, you reveal some information about that and prove that like, yeah, that is a country that actually signed on this like passport. Okay, and let me kind of quickly go over the technology. The reason why this is become like very practical and possible today have a lot to do with the like technical like advancement. DeCo is actually the first paper that talked about how to use like incredibly ZK. At that time, actually more about MPC and like Snark to kind of verify this like web data. And you have 2 parts, MPC and like needs. And the MIZK part being replaced by IZK and later being optimized using like Quicksilver, which start to use low-degree polynomial. You can multiply that. It's about 300 times improvement. The MPC part have a 15 times improvement by a recent paper that basically replaced the MPC with semi-honest MPC plus IZK, because they discovered that like I would say that the malicious security MPC and semi-honest security MPC and IZK have different security guarantee, but they find that in that use cases, this is good enough. Okay, got it. Okay, so concurrently, there is also a lot of the like adoption in the industry. Brave browser have recently an e-print on that. I don't know when like Brave browser will actually provide this functionality as well. And TLS Notary, they are a recipient of like Ethereum Foundation's like grant. They have been working on this probably already for 9 years. And like now I think they are writing like the entire stack using Rust. Okay, and this can be useful for KYC, and you can also use that for even for real world like assets. Okay, and the good thing about like interaction being a requirement is that you can actually offer deniability, because if the interaction is not happening in front of you, you cannot believe that. Okay, I think I will just almost like skip this one, but basically is that like IZK can be also useful for like performing like data analysis when you want to like test some distribution. And like, well, Ben do like federated learning for anti-money laundering. And that like, when data are being used in that case, we want to make sure that the data is balanced, because when the data is not balanced, some different group might actually not receive a correct decision. And this is more about a fairness problem. To ensure distribution testing, we have a paper that actually basically talk about that. You can use IZK which quickly reduces the overhead by about 200 times. You then use some technique that is only possible in IZK, you get about 10,000 times improvement. I a little bit dare not to write this number because it would be very weird, but this is basically what is possible, is that by just using IZK and then think about what technology that you can build with in IZK, you can actually have very significant performance improvement because you are basically changing the algorithm that you are actually doing a lot of the testing. So some future direction, like hardware acceleration. Why? Because when IZK bring like Web 2 thing to the Web 3, we don't want to bring, well, we don't want everything the Web 2 to come here. Because think about this, especially people know what code is actually kind of scanning people's eyes, right? A lot of the people are already waiting online for that. When you have interaction, it might take times. And here is the bad example. You don't want people who are using interaction to do KYC to have to sign up and wait outside in order to connect to a server to have to do that, right? So there is actually a demand for accelerating the IZK because the verifier might become a bottleneck here. Okay, another thing which is more academical is that in IZK, we want the user to be able to prove to multiple party. And the best way to do that is that you try not to let the user do n times the work. The only way to do that is to use MPC. This is an academic research copy that no one have done before, and we don't know how the overhead would be. But it would be an interesting question. Basically, instead of let a user talk to everyone, you let that 6 party simulate 1 party in the MPC. Okay, and the last note is that IZK is actually mostly post-quantum. So this actually, if you combine that with other advancement that we see in browser in the web, is that our internet is moving to a post-quantum time, and that IZK is also post-quantum. This might actually give you a verifiable web, which is completely post-quantum. Post-quantum is now, also post-quantum is not slow. People might have the feeling that post-quantum is expensive. Kuiper, which is the new protocol, should be actually faster than the one that we are using today. So we should expect that more of this application-specific IZK protocol for post-quantum crypto, and this might actually enable new application. And so if you want the slide, if you want to talk to me, you can scan the code. And here, this is all my talk. And any questions?
Wow, that was a lot of buzzwords, especially post-quantum repeatedly. It's nice that we've had a second day with these. I see a hand there with Opal already, and Mr. Jonathan also.
So one of the things with Quicksilver, that actually can be made non-interactive. It looks like for the performance comparisons, you weren't so much comparing interactive versus non-interactive, but interactive ZK versus ZK snarks. Is that about right?
I think Quicksilver would not be able to be made non-interactive, right?
I pulled up the paper and it actually mentioned being able to be made non-interactive via the Fiat-Shamir transform.
But you need to deal with the offline phase, right? The online phase can be made non-interactive, but the offline phase cannot.
Okay.
Yeah.
Okay, sorry.
Yeah. But you are right, and that's the optimization that they use.
Hi, yeah, thank you for the talk. Just a very quick question about the hardware acceleration at the end. I know there's a lot of companies doing hardware acceleration.
You are the inventor of a lot of the technique here, right? So basically, I think it's almost completely different. So one thing that we see is this. Yeah, I think it's very different, right? First of all, the field is different. Second is that I think it's also the problem is about this is that many people assume that you only need to accelerate the offline phase. That's not true. Offline phase now is almost just 1/3 of the computation. And if you are considering the online phase and considering that this circuit may actually be very different from each other, you have different application, I would say this is a very different problem from the SNARK. Yeah.
Any counters, any questions? I see one here.
Thank you for the interesting talk. Just want to see if you can maybe give an example of implementation for federated learning? Are there any kind of company that's actually working on implementation? Per se?
Yeah, so so you can add me and I can send you a link. I think at this moment, mostly are really like this company talking to, like, for example, banks. So these are more like really commercial application, but mostly with financial institution. That seems to be very interesting in this technology. But open source development, and also, by the way, a lot of these companies, even dare not to talk about what is the party that they are collaborating with. So Intel mentioned that they collaborate with a big bank, not mentioning what that is. Yeah.
Maybe you can click a picture of the links and then get in touch with him, perhaps, yeah. I think that's it for this session. Thank you so much, Weikeng. Thank you for your time.